So, last class we have discussed that if we have an unconstrained optimization problem is there, we can solve it by using the KKT condition, and we have discussed the KKT necessary conditions. Agree? So, next is a sufficient condition, whether that point regular point is a minimum value of the function will give you or the maximum value of the function will give you, that will be decided by using the sufficient condition. So, let us call that the second order sufficient conditions. KKT. So, suppose that x star is the feasible point. Feasible point means the point which is lies in the what is called feasible set, and at that point that equality constant and inequality constant must satisfy. So, that is the feasible point. Suppose x star is a feasible point for the constraints it must satisfy these constraints is equal to 0, and we have a there are p equality constant as well as it should satisfy the inequality constraints less than equal to 0 for j is equal to 1 to dot dot m. This now question is, if there is a if there exist, this is called there exist vector, this symbol is there exists a vector lambda star, it is a Lagrange multiplier. What is this one? Lambda 1 star, lambda 2 star, dot dot lambda p star, because there are p equality constants are there. If there exists vector whose dimension is p cross 1 and mu whose dimension is m cross 1 is equal to mu 1 star mu 2 star dot dot mu m star. If there exists this and this vector, so that KKT condition, that KKT necessary conditions satisfied, condition satisfied. What is the necessary condition? Gradient of Lagrangian function must be equal to 0. So, what is the gradient of Lagrangian function with respect to x? If you see that L, gradient of L with respect to x is nothing but a gradient of f of x, this plus summation of I, that is we have shown last class, that is equal to lambda I star gradient of h I with respect to x, this plus summation of that is j is equal to 1 to m gradient of this x g j x star, this must be equal to 0, whose dimension is n cross 1, whose dimension is n cross 1. Agree? This dimension is n cross 1. So, and also there are which is called switching function must satisfy mu I, mu j, g j x star j must be equal to 0 for j is equal to 1 to m, and mu j is the Lagrangian multiplier associated with the inequality constants, mu j must be greater than equal to 0, that we have shown last class 1 to dot dot m. So, this is less than equal to greater than equal to 0 when the constant will be this type of constants are less than equal to 0, then this will be greater than equal to 0. Agree? Non-negative non-negative, mu is non-negative, that we will see later in our discussions. So, this is the thing R satisfy, and for any vector, for any, you see this so that the necessary conditions are satisfied, this condition is, and for any vector z, any non-zero vector, rather you write it non-zero vector, any non-zero vector z whose dimension is n cross 1 satisfying the following conditions. What is these following conditions? The gradient of G j of x star with respect to x, this multiplied by z transpose, okay, this must be equal to 0 and mu j star equal to greater than 0, this is greater than 0 for all active inequality constants, for all active inequality constants. For all active equality constants means if x star is a your regular point, then at that point that inequality constant, if it is a at that point G j of x is equal to 0 at x is equal to x star, where x star is the regular point, then it is called the active constants. Okay? Because I mentioned it, we have a inequality constant is small m. Out of small m, if at regular point, if it is small l is the number of equality constants satisfied, and remaining small m minus l is the satisfy the that inequality conditions. I is equal to 1 to j is equal to 1 to dot dot l, and j of x star is less than equal to 0 for j is equal to 1 to dot dot m minus l constants. These are called active equality constants, and these are called the inactive equality constants. This. So, this condition must be there. Naturally, when this is greater than 0, then g of j is the your active constants, and gradient of that at that point x star, gradient of that point with any vector, if you multiplied by this transpose of this one, this must be equal to 0, because that are one is tangent, another is perpendicular to that one. So, this is a orthogonality condition is must satisfy. Next is z transpose gradient of x g j of x star is less than equal to 0 when mu j and mu j star equal to 0. So, this constant when mu j g j is inactive constants, okay, at that condition this quantity will be less than equal to 0. And next is similarly in equality constants, that with h z transpose gradient of x with h I of x star is equal to 0 for all constants. This is for all constants h I x star is equal to 0. This is the all constants for active inequality, means when g j of this is 0, these conditions. This is for inactive constants, this. That means, if you have a, let us call constant, this is one constant is there g 1 of x, this constant, and another constant is like this way g 2 of x. Agree? At this point the function value is 0. Now, what you find out the gradient of at this point because these equality constants are satisfied. At this point you will find out the gradient. That means, you draw the tangent corresponding to this curve here, and perpendicular to this one is the gradient of g 2 of x. This is, and here corresponding to this curve, draw a tangent, and perpendicular to this one is the gradient of g 1 of x star. So, that direction z tangent of this one is z. Z transpose of this must be this equal to 0, that one. Similarly, H case also you can show it. So, this is all constant for I is equal to 1 to dot dot p. So, if this is the satisfy, then this point will, that point x star will be a, then point x star will be a what is called negative, that if the following constraints, because we are finding out the sufficient conditions, if the following constraints is true, that means z transpose, z is any vector, is that second partial derivation of derivative of f of x at x is equal to x star, this plus summation of I is equal to 1 to p. This is nothing but a just like a unconstant optimization. We have done the second derivative of the function, that is Hessian matrix must be positive definite for minimum value of the function. Hessian matrix must be negative definite for maximum value of the function. Similarly, this our now the function is unconstant function is Lagrangian function. The Lagrangian function, similarly second derivative of this one with respect to x, what we are getting it is that lambda I star gradient of x h of I of x plus summation of j is equal to 1 to m mu j star gradient of x square g j of x star into z greater than 0. Greater than 0 means it should be a positive definite. This indicates this matrix, this is a matrix of dimension n cross n. This is a symmetric matrix of dimension n cross n, and this quantity will be positive definite provided this matrix is positive definite. So, our condition is this must be, in order to get, in order to x is equal to x star should be a minimum point, agree, then this must be a positive definite matrix f of x star plus summation of j I is equal to 1 to p lambda I star gradient of this, not gradient, second derivative of this, my Hessian matrix of H, agree. So, this is a star, this plus summation of j is equal to 1 to m mu j star g j of x star. This matrix must be greater than 0, means it should be a positive definite. Then we will call x is equal to x star, we will give you the minimum value of the function, agree, and that point is a isolated point, that point is a isolated point, optimum point. Isolated point means near around this point there is no other minimum value of the functions, agree. So, this is a, you can say isolated point means there is no other around this point will have a minimum value of the function. So, this is the isolated point of this function. So, how to calculate this one, you know this, that is if you write more clearly that or isolated point means there is no other local minimum point in the neighborhood of x star, agree. The isolated point, once again I remain, isolated point is means that there is no other local minimum point around x star, around that x star. So, let us see how to calculate this one x star, that is Hessian matrix of f of x at x is equal to x star. How will you calculate this? If you recollect, this one is nothing but a delta square of f of x del x 1 del x 2, sorry, del x square, del square of f x, then del x 1 del x 2, and since we have n variables are there, then we will get del square of f x plus del x 1 del x n, and similarly you can write it that del of x square del x 1 del x 2 and del f of x del x 2 square, and in this way del square of f x del x of 2 del x n, and if you continue like this way, last term will be del f square del x 1 del x n, then del square f and del x 2 del x n, and last term is your del f square x del x n square. So, put these values at x is equal to x star. So, you have computed, and similarly if you see this one del x, that is Hessian matrix of H 1, it varies from I is equal to p H 1, you will get a matrix, you will get a matrix of dimension, say with respect to of dimension n cross n. So, this dimension is n cross n, agree. So, similarly I am not writing this one del square f h I of x, you can get it in similar only you can say f will be replaced by h I, this f will be replaced by h I function, then you can write it, this is also n cross n, and you have to put the value x is equal to x star, agree. So, I have just write it first for you, that h I of x del x 1 square h del I of x, then del x 1 del x 2, and in this way del square I of x del x 1 del x n, and in this way last is del square I of x del x 1 del x n, and if you do this one, last one is del square I of x del x n square. So, okay, this is the second part of this sufficient conditions we have written all I. Now, here we have to write it, if you see this one, here you have to write it I varies from 1 to dot dot p. Similarly, you can write it delta x that g j of x. So, I will not repeat, only in place of f you replace by g j, and that is also n by n matrix, put the value x is equal to x star, and it is also symmetric matrix. Once you do this one, next is you have to check this matrices you know, this matrices you know, this matrices you know, add all this together, you will resultant you will get another matrix. So, you will see whether that matrix is positive definite or not, and you know how to test the positive definite matrix or not by Sylvester equality constraints, equality conditions, or you can find out if a matrix is positive definite matrix, then you find out its eigenvalues of the matrix. If all the eigenvalues are positive, then it is a positive definite matrix. If all the eigenvalues are negative, then it is a negative definite matrix. Similarly, positive definite matrix, if that matrix, you find out the eigenvalues of this matrix, if some of the eigenvalues are positive, some are what is 0, then it is a positive semi definite matrix. Similarly, negative semi definite matrix case also you will get some of the eigenvalues are negative and some of the eigenvalues are 0, at least one will be 0. So, once you know all this one, then I can find out the second order sufficient conditions. Again, if this matrix is positively definite, we will call it is a what is called the function will give you the minimum value of the function, and x star is the isolated point. Isolated point means this that the function does not have any other local minimum point around that x star. So, let us now solve a problem, then how to work out these problems using the our technique, that what is called constraint optimization problem, how to find out. So, our problem is minimize example, minimize f of x is equal to x 1 square plus x 2 square minus 4 x 1 minus 6 x 2 subject to constraints x 1 plus x 2 is equal to 2 x 1 plus 3 x 2 is less than equal to 12, and we are assuming that our side constraint x is greater than 0 and x 2 is greater than 0 this. So, this problem you have to solve it by using KKT conditions. That is our problem. So, what is our job? This is our equality constraints is there and inequality constraints, both are, let us call both are inequality constraints. Agree? This are inequality constant, this are. So, we do not have any equality constraints. So, in that case h I of x is equal to 0, that lambda is associated with the equality constant. So, Lagrange multiplier lambda I will not be there in our solution. Agree? So, let us say first you write it the solution of the problems. So, let us call first we write it the necessary conditions again. So, first we write the Lagrangian functions, that function f of x plus summation of, there is no h equality constant. So, that term will not come into the picture, there is a inequality constant j is equal to 1 to m, in our case m is equal to 2. There are two inequality constants if you see here, this and this. So, 2 then mu j, then our inequality constant we have converted into a equality constant, that is if you see g j of x plus s j square, this one. So, now I use the necessary conditions for this one. So, I will find out del L del x 1 is what is equal to 0, because so what is this one f of x, you see f of x is that one. So, you differentiate with respect to x 1. So, it will be 2 x 1 minus 4. So, it will be a 2 x 1 minus 4, and we have a also, if you see this one, or okay, I write it, then it will be clear instead of calling this one. What is f of x? It is a x 1 square plus x 2 square minus 4 x 1 minus 6 x 2 plus mu 1 g 1 of x. G 1 of x is equal to what? You see g 1 of x is equal to x 1 plus g 1 of x is equal to, you see if you call this is g 1 of x, x 1 minus x. So, I can write it this, if you see this one, I can write it this g 1 of x is equal to x 1 plus x 2 minus 2 less than equal to 0. So, this is our standard form we have written. Similarly, this is also we can write g 2 of x, we can write it, okay, write it this one, g 2 of x is equal to g 2 of x, we can write it is equal to 2 x 1 plus 3 x 2 minus 12 is less than equal. So, we have written our standard form type less than equal to form. So, our g 2 1 g 1 of x, if you see x 1 plus x 2 minus 2, and we are adding with a some positive quantity. So, that it will turns out to be a equality constant plus mu 2, then 2 x 1, that G 2 is your 2 x 1 plus 3 x 2 minus 12 plus S 2 square. Agree? Now, I am differentiating this with respect to x 1. So, it will be a 2 x 1, 4 x, then here is x 1 is there, mu 1, and no other x is here, here again is there is 2 mu 2. So, this equal to 0. Okay. This is one equation. Again you have to differentiate with respect to x 2. So, if you differentiate with x 2, this is 2 x 2 minus 6, then it is a plus mu 1, then plus 3 mu 2, because I am differentiating with respect to x 2 mu 2, agree. Then this is 0 with respect to this, with respect to x 2. So, these zeros, then this is the one equation. Let us call this is equation number 1, this is equation number 1, and this is equation number 2. Agree? And we have a, in fact, we have to differentiate L with respect to, there is no h. So, we need not to differentiate with respect to lambda. So, we have to differentiate with respect to our mu, and another thing L we have to differentiate with respect to S. We have shown it that these two conditions can be combined together, and finally, we can write it that condition is mu I g j of x is equal to 0, and our case j is equal to 1 and 2. Okay. So, what is this condition? We will write it mu 1 g 1 of x must be 0. Another condition is that mu 2 g 2 is 0. So, we have you have to solve these two equation. We have how many unknowns are there? X 1, x 2, mu 1, mu 2, and we have 4 unknowns, 2 equation, and from there we have to see how to solve it. Look at this one, that there is this has a 2 possibilities to satisfy this condition. One condition is mu 1, if it is a mu 1 is 0, and mu what is called g 1 is not equal to 0. Another choice is g 1 is 0, but mu 1 is not equal to 0. Okay? When mu 1 is not is equal to 0, g 1 is not equal to mu 1 is equal to 0, case mu 1 is equal to 0, g 1 is not equal to 0, that means it is a inactive conditions. When mu is g 1 is 0, but mu 1 is not equal to 0, but this condition is satisfied, in that situation it is called active condition is satisfied. Similarly, you have this. In general, if you have a m small m number of inequality constant, we have a 2 to the power of m possibilities are there to satisfy this equation. Again, 2 to the power of m possibilities are there, when switching, we can switching 2 to the power of m switching is possible to satisfy these equations. When that we have a j is equal to 1 to m, that means m constants are there. So, in short, if you have a m constants are the inequality constants are there, then we have a such type of equation, we have m equations are there, which in turn we have a 2 to the power of m switching conditions are there to satisfy these equations. So, let us solve for this case. So, our first case we are considering that case 1, mu 2 is, let us call 0. If mu 2 is 0, then g 2 cannot be 0. Agree? So, g 2 is, our condition is g 2 is less than equal to 0. So, equal to cannot be. So, it is this. So, it is the inactive conditions. The condition is more relaxed. When it will g 2 is equal to 0, it is an active condition, that means it is a more tightened conditions. That means it should be on the curve or on the line. If it is g x is a straight line, then it should be on the line only. when g x is a active condition 0. So, we have a this one condition mu is 0, then we can get that g 1 is 0, g 1 of x, g 1 is equal to 0, but if g 1 is 0, mu 1 is greater than 0. Both cannot be 0. Mu 1 g 1 mu 1 is equal to 0. If this is 0, it is enough to satisfy that conditions. So, in this case, that means mu is 0, g 1 is 0. Agree? In this case, what is this situation? We will see from 1 and 2. So, from 1 and 2 equation, I will put our, if you see mu 2 is 0, mu 2 is 0, and there is a constraints are there g 1 is 0. So, we will put mu 2 is 0 from 1 and 2, then we will get it 2 x 1 minus 4 plus mu 1 is equal to 0. Another equation will go 2 x 2 minus 6 plus mu 1 is equal to 0. This is, and we have a g 1 is 0, g 1 is what, x 1 plus x 2 minus 2 is equal to 0. So, we have a 3 unknowns are there, we have to solve these 3 equations. By solving this equation, we obtain x 1 is equal to half or is equal to 0.5, x 2 is equal to 3 by 2 is equal to 1.5, and mu 1 we got it 3, and mu 1 must be, I told you when it is a g 1 is active constant, mu 1 must be positive non negative number. If it is, you get it by solving this one negative, that means it does not give any solution for to become a what is called optimal value of the function. So, this must be, this is 3 means greater than 0, and mu 2 is equal to 0. Again, this we got it. Now, we have to see whatever this point is, it must satisfy all feasible conditions, I mean all inequality conditions. Okay? And equality conditions, if it is satisfied, then we will call the point is in the inside the feasible space or feasible set or feasible region. So, let us say feasibility check. So, our g 2 we have to check it now, g 2 of x, if you say g 2 of x is what, twice x 1 plus 3 x 2 minus 12. If you see the g 2 of x our expression, and this we have to show it, it is our condition must satisfy, our condition is less than equal to 0. So, this condition if you put the value of x 1 is equal to half, value of x 2 is equal to 3 by 2, then what we will get it, that one we will get what is called this is half, half means this is 1 and this is 3 by 2, 3 by 2 means this is a 9 by 2 means 4.5 minus 12, and that is less than 0. That means 5.5 minus 12 is less than 0. So, this satisfies this condition. So, this point may be one of the what is called point which will may give the your minimum value of the functions. Agree? So, that we have to check it next. So, how will you check it that one? So, this satisfy all what is called constant equation at this experiment, that x 1 is half and 3 by 2 it satisfy all constants. Agree? So, we can see this is the solution, Agree? That means x 1 is x 1 star is equal to half, x 2 star is equal to 3 by 2 is the solution. Agree? Now, here also you can check it whether it is the minimum value of the function or maximum value of function without checking the sufficiency conditions, and that condition we will call that how to check that one, let us see. So, let us call f function at x is equal to x 1 is equal to x 1 star and x 2 is equal to x 2 star. Agree? This value is I know x 1 plus x 2 minus 4 x 1 minus 6 x 2. Put the value x 1 is equal to half and x 2 is equal to what is x 2 star is equal to 3 by 2. If you put this value of this one, you will get this value is 8.5 this. So, this you got it. Now, how you say this is the you got the value of the function at that point, but how do you ensure that this will give you the minimum value of the function? One can check these things by using the monotonicity analysis, that is monotonicity analysis. What is this? I also we have discussed you earlier that at this point you give a small perturbations. If it is a minimum value and you give a perturbation around this point, the function value if it is a increase then it indicates we have reached to the minimum value. Okay. So, this is called the monotonicity analysis. So, what is this? Let us call we put the value of the function x is equal to this at x 1 is equal to, let us call we have found this value at x 1 is 1.495 instead of what is called that finding out the x 1 is not, this is x 2 is 1.1 instead of 1.5 I am writing 1.495 x 2. That means, what is the change I made it 0.005 and x 1 I made it let us call 0.505. 0.005 added and from 0.005 is part of it from this one, and if you put this value at this one you will get that value is 8.4995. That means, function value is increased from minus 8.5 it is a minus 4.5, it increased. If you see in the dimension x 1 and x 2 dimension, x 1 and x 2 dimension, if it is 8.5, agree, this is corresponding to 8.5, this is 8.5, agree, then this is 8.495, agree. That means, this function value is increased from here to here. So, this indicates this is what is called give a minimum value of the function. Also, we will check through what is called necessary sufficient condition of KKT condition. So, case 2 may be case 2. Case 1 you see we have made it case 1 mu 2 is 0, I will make it mu 2 is 0. Now, there is another possibility is there that mu 2 mu 1 also 0. So, our case keeping mu 2 0 same, that means g 2 of x is less than 0 and we are making that mu 1 is 0, that means g 1 of x is less than 0 this. So, again from 1 and 2 we can write it twice x, I will put the value of mu 1 and mu 2 in that equation 1 and 2 equation. So, I will get twice x is equal to 4. So, x 1 is equal to 2. So, twice x is equal to 6, x 2 is equal to 3. So, I have to check this value I got it. So, I have to check the feasibility conditions and mu 1 mu 2 is 0 feasibility conditions. Okay, I have to check the feasibility condition. What is the feasibility condition? G 2 of x I have to find out, g 2 of x I have to find out at x 1 is equal to 2, x 2 is equal to 3. Agree? Let us see this one. What is g 2 of x? If you see this one, x 2 minus x 2 plus 3 x, sorry, x 2 x 1 plus 3 x 2 minus 12. Agree? So, this is our g 2 of x. Put this value x 1 is equal to 2, x 2 is equal to 3 and you will get this value is 13 minus 12 which is not equal to which is less than is not less than 0. This indicate not less than 0, this is means this is equal to 1. So, it does not satisfy this one. That means, we have a point 2 and 3, this is outside the feasible region, okay? Feasible space. Similarly, 1 is enough to check, that means, this is not the acceptable solution here. So, you can also check g 1 of x at x 1 is equal to 2, x 2 is equal to 3, and in this way g 1 of x, you know, x 1 plus x 2 minus 2, put the value of x 1 is 2, x 2 is equal to 3. So, x 1 is a 5. So, it is a 5 minus 2, which is not less than 0, which is not less than 0. Okay. So, so these two condition g 1 so our conclusion is that g 1 and g 2, the g 1 of x and g 2 of x at x 1 is equal to 2, x 2 is equal to 3 violates the conditions. So, our conclusion then, this is not the our condition, that this indicates, this implies the x 1 is 2, x 2 is 3 is not, does not belong to feasible space. This does not belong to a feasible space or design space. Okay. So, this case 2 will not be acceptable, that way. Case 3, in other words, is not feasible space, there is no solution at that point. So, case 3, now I made mu 2 is 0, agree. Then this another possibility is you make it mu 1 is 0. If mu or 0, g 1 of x is less than 0, then you have a g 2 of x, g 2 of x is equal to 0. That means, mu 2 greater than 0. Agree? So, this greater than equal to 0, this. So, let us see this one, mu 1 is 0. So, from equation 1 and 2, from 1 and 2, I will put mu 1 is 0 in this. Okay. So, I will get it once again, if you see, I will get twice x 1 minus 4 plus mu 1 is 0, so twice mu 2 is equal to 0. From equation 1, I will get this one, putting mu 1 is 0. From equation 2, 2 x 2 minus 6 plus 3 mu 2 is equal to 0, I will get it. And we have a g 2 is 0. G 2 is what? If you see G 2, our 2 x 2 sorry 2 x 1 plus 3 x 2 minus 12, agree, G 2 is 0, this one, that may active constant, this one, this. So, solving, we have a 1, 2, 3 unknowns are there, 3 equations there. Solving this, we get x 1 is equal to 1.846, x 2 is equal to 2.769, and mu 1 you have considered is 0, and mu 2 is, we are getting is 0.31, which is greater than 0. Agree? So, this satisfies all the conditions. Agree? So, this may be a one of the possible solution to get the minimum value of the function, but first still we have to check it either what is called monotonicity analysis or using the what is called by KKT second order conditions. So, let us check the feasibility conditions. Our feasibility condition is, this condition must be satisfied, G 1 is less than 0, this must be satisfied. So, our feasibility conditions, if you see this one, our feasible condition G 1 of G 1 of x What is G 1? X 1 plus x 2 minus G 1 x is minus 2 I think. So, put the value x 1 is equal to, that we got it, x 1 value is how much we got it, x 1 we got it, if you see this x 1 is 1.846, x 2 is equal to 2.769. So, if you put this one, G 1 is, you see, does not satisfy. So, it is a 1.846 plus 2.769 minus 2, which is greater than 0, agree, which is greater than 0. So, it does not satisfy the our monotonicity analysis, what is does not satisfy our constraints, this must be less than 0. So, this cannot be a, once again this cannot be a G 1 of x violates the condition. So, the point x 1 is equal to 1.846 and x 2 is equal to 2.769 cannot be a solution of our optimization problem, because it does not belongs to in feasible region, feasible space. This point is not belongs to feasible space. So, reject that solutions, agree. So, you see this one, our case 3, what we made it your case 3. Case 3 is that one we made it, that G 1 is 0, naturally G 1 into G 2 must be 0. So, this will be less than 0. So, this equation G is coming from equation number 2 and 3, putting mu 1 is 0, this, then I have G 2 is 0, this. So, solving this equation I got this. So, it must satisfy this equation, and when we are putting this equation we got it, that one, it does not satisfy this one. Now, case 4, what is the choice is left now, that G 1 is 0, mu 1 I made it 0, G 1 of is G 1 is equal to 0, which means mu 1 is greater than 0, and next choice is left, G 2 is 0, that means mu 2 is greater than 0, agree. So, let us say using this equation in from 1 and 2, what we will get it, 2 x 1 minus 4 plus mu 1 plus twice mu 2 is equal to 0. This I am getting from equation 1, agree, and then from equation 2 I am getting is 2 x 2 minus 6 plus mu 1 plus 3 mu 2 is equal to 0. So, this is you are getting from equation 2, this one. Now, so this we have a how many variables are there, x 1 x 2, then your x 1 x 2 mu 1 mu 2. So, you have a 4 variables are there, agree. So, now use these conditions, because this is the we consider G 1 is 0, G 1 of this 0 means G 1 is what, x 1 plus x 2 minus 2 is equal to 0, agree. So, this and G 2 is 0 means that is 2 x 1 plus 3 x 2 minus 12 is equal to 0. So, you have a 4 equations are there, 4 unknowns are there, mu 1, mu 2, mu 3, mu x 1, x 2, mu 1, mu 2. So, solving this equation, solving the above equation we get, agree. Solving the above equation, what we will get, or you see this one, either this you can first you solve this and this. This is a variable of two variables g 1 x this, you have a two variables two equations. So, I can solve this, or you can write it solving we get solving these equations we get x 1 is equal to minus 6 and x 2 is equal to 8, agree, and it does not satisfy our what is called our side constraints. We have put it x 1 is greater than equal to 0, x 2 is greater than 0. So, let us call and solving the other two equation, solving the other two equation, other two equations, agree, solving other two equations, or you just write it solving other two equations, we get mu 1 is equal to 68 and mu 2 is equal to minus 26, which is not greater than 0, which is not greater than 0. So, it also violates our what is called Lagrange multiplier conditions. There are side constraints are violated, and our what is called that Lagrange multiplier for inequality constraints that should be positive, but it is become negative. So, mu 2 violates the conditions. So, no solution at this point. What is this point? X 1 is equal to, we got it, x 1 is equal to minus 6, x 2 is equal to 8. Not only this, you can stop it here, because this does not satisfy our side constraints. So, now if you see out of the 4 cases, now in short, if you have a if you have a small m inequality constant, you have to solve the 2 to the power of m cases for considering the switching possibilities cases. Out of this, you have to search on which one will give you the feasible design space or feasible solution, and at that point whether it is a minimum or maximum, one can check by monotonicity analysis, or you can check by considering the second order KKT conditions. So, if you see that second order conditions, so our acceptable things is check. Our acceptable x 1 is equal to 0.5 and x 2 is equal to 1.5 star. Agree this. So, you have to check the KKT conditions, second KKT conditions. What is the second order KKT conditions? F of x, this f of x plus summation of j is equal to 1 to 2 mu j del f del x g j of x star, as this star. Agree? So, this you have to go, because we do not have any equality constraints. So, these two things you have to find out. So, let us call what is f of x is our x 1 square plus x 2 square minus 4 x 1 minus 6 x 2, and what is g 1 of x is equal to x 1 plus x 2 minus 2, g 2 of x is equal to 2 x 1 plus 3 x 2 minus 6. So, find out the this of this at x 1 is equal to 0.5, x 2 is equal to 1.5, agree, and this will come, if you do this one, it will come 0 0 2 0, and this second derivative of g 1 of g 1 of x star with respect to x, you will get a null matrix, agree, and similarly g x of g 2 of x, you will get a null matrix. So, add these matrices, and ultimately you will get this one. So, this is positive definite matrix. So, 2 0 0 2 is a, this matrix is a positive definite matrix by using Silber's theorem. So, our conclusion is we will get the optimum value, means minimum value of the function at this point, and corresponding mu is what? If you see that corresponding mu of that one is that mu, you just say that mu, you got it positive quantity. If you recollect this one, mu 1 is equal to what and mu 2 is equal to what, you will see is a positive quantity. So, we will stop it here. Next class we will discuss some of the issues related with the what is called parameter variation in the objective functions, effect of parameter variation in the objective function. Thank you.